Okay. We are barreling toward the end of context-free languages and context-free grammars. There's one big important topic left to cover, and that is the actual automata representation of this. So we'll get to that. We'll talk about the all-important CYK algorithm that I've hinted at. And we're almost there. We're almost through this section. And so there are three big main sections of four big main sections of automata theory. There's regular languages, there's context-free languages, and then there's everything that the modern computer can compute, which we will study through Turing machines, which are basically a theoretical representation of a computer. And then we will barrel into a really interesting theoretical topic of what are the theoretical limitations of what an arbitrarily powerful computer could compute. There's the practicality of how powerful are our computers today. And then there's the concept of if we had an infinitely powerful computer with infinite RAM and infinite speed, what could we still calculate and not calculate? Which is a really interesting problem. And then after we've done all of that, we will talk about the exact implementation of compilers, and we'll have all of the background material to talk about things like LL parsing, LR parsing, lexing, all of the fun problems that compilers bring to us. So that's where we're headed. You can expect an assignment later today that we do next week on all of the stuff that we plan to cover before Friday. Last time we talked about some ambiguous languages. We talked about ambiguous grammars, but this concept was basically that the language itself can be ambiguous, which means that it's not possible to build a context-free grammar that represents the language. It's not just the grammar could be ambiguous or non-ambiguous. It's that we can show that no such unambiguous grammar exists. So this was the example that we used. We had a union between two context-free languages, A to the N, B to the N, C to the M, union A to the N, B to the M, C to the M. We came up with two different grammars, one of which represented the left-hand side of the union, one of which represented the right-hand side of the union. And we had one rule that we could use to combine them. And the intuition behind why this is context-free and also why this could never have a grammar written for it that was unambiguous is that we need to make the decision in the grammar immediately, are we in the left-hand side of the union or the right-hand side of the union? And if we're actually analyzing a string character by character, we're not going to know from the first character whether or not we are in the first case or the second case. And if we're in the left-hand side of the union, the way that we would handle this with something like a stack is we would push a bunch of A's, and then as soon as we see B's, we would pop the A's. And then we would do nothing with the C's because it doesn't matter how many C's there are. We just need there to be an equal number of A's and B's. So if at the end of this string, the stack were empty, meaning we'd seen the same number of A's as B's in that order, then we could terminate with success, saying we can represent that language. On the other hand, on the right-hand side, we ignore the A's at the start. And as soon as we see some B's, we push some B's onto the stack. And then as soon as we see C's, we transition and start popping the B's off the stack. And if the stack ends up empty, then there were an equal number of B's and C's. So we have ways to do this in a context-free world. There's a grammar to do this, and I'm trying to phrase this in the form of a pushdown automata so that we start priming ourselves when we introduce the concept of a pushdown automata. But so we can represent both of these with just a stack structure. However, when you see that first A, do you know if you need to keep track of the A's or not? It's difficult. You can't come up with it in the realm of the rules that are able to be done with a pushdown automata. You could write an algorithm that would solve this. But this is when we get into Turing machines. Any algorithm you could write could be represented by a Turing machine. So you could solve this problem. Does anyone have any intuition if you were to write a program to recognize this language, what you would do? As soon as you have a second stack, it's nice and easy.
Just count the number of A's, check if the number of B's matches, and then count the number of C's.
Yeah. Yeah, even if you had two stacks, you could push the A's onto both stacks. And then when you start seeing B's, you only pop the A's from one stack. And then you push the B's onto the second stack. And then when you see C's, you pop, and then you would look at the top character. And if the if the left stack is empty, or the right stack's top character is an A, then you accept. So with two stacks, it's very possible. But without that second stack, we have to make a decision before we know where we are. Which is why it's not context-free. All right, rather, why it is context-free, but why the grammar is ambiguous. All right, so we're going to apply this a bit to programming languages. So we want to be able to start writing grammars rather than talking about A's and B's and C's and things that aren't quite as useful to programming languages. If you're actually going to go read a programming language grammar, what is it going to look like? So of course, we know we can define programming languages with grammars. And if we do this, they're most frequently done using a particular kind of grammar called a BNF, or it's a grammar that's in Backus-Naur form. We can dive into that a little bit if we have time at the end of the class. But so we can look at it as something like this. Stop it. There we go. Put that in the wrong place. So we have new ways of referring to arrows in BNF, which is : equals. And : equals just as a defined by. So just as before, we had that E and that T and that F in the as non-terminals in the grammar defining expressions. And now we know what they stand for. The T's stand for terms, the F stands for factors. And we can now start to define. And now we see non-terminals are also words rather than just symbols, but they're also encapsulated within these angle brackets. The angle brackets specify that we have a non-terminal. And then anything not in that is a terminal. This helps make the production clearer. This helps you to ground yourself within the actual programming syntax and programming rules. So an actual example of this using programming language syntax would be something like this. Where are the terminals? Where are the non-terminals?
Is while a terminal?
While is a terminal. What does that represent in a programming language? A keyword. So now we know why keywords are reserved in a particular language, is they're reserved to be terminals in the grammar, whereas variables, anything that could be a variable is reserved to be a non-terminal because at the time of compilation, we don't know what the value is going to be. So that's kind of an interesting thing that maybe you were taught in programming 1. These are keywords, you can't use them as variable names. And this is the actual theory behind why. So this looks like a basic grammar production, right? We have a single non-terminal on the left-hand side, and we have an expression based on terminals and non-terminals as the definition on the right-hand side. So if we could tokenize some program and see this terminal symbol while, and we have something that matches the form of an expression, and we have something that matches the form of a statement, then we could map that entire block of code as a while statement. So we've defined a level of abstraction in programming that has to do with a sequence of terminals and non-terminals that we define in the grammar. This allows the compiler to parse the code and be able to determine whether or not it is syntactically correct. So keywords make the compiler's work significantly easier as well, because otherwise there would be no real reason or way to tell if we had an expression followed by a statement that would not necessarily by itself dictate that that is a while statement. You need the keyword while to tell us what the user wants us to do with that. It should be parsed as a loop. So here's a very high level question that you shouldn't necessarily be able to answer at this point, but is a very important question to the theory of computer science and being able to design languages for programming. What grammatical rules can we permit and be able to parse efficiently? We want to give the end user as much power as possible in the language, right? We don't want to restrict what they can and can't do more than necessary. But we also want to be able to efficiently parse a program that they write so that we don't sit there spinning our wheels at the compilation step for a very long period of time. So this gets into the LL and LR grammars that I was hinting at a few minutes ago. When we discuss compilers, that will be the big question that we answer. And I actually will go into a little bit of detail. I'll be sprinkling these details throughout to kind of prime you for the discussion that we're going to have when we get to that technical section. But it's really interesting to be able to see what can we parse efficiently and how does that lead to the kinds of programming languages that you've been programming in. This may be a question you can answer. If we take and break down a programming language a bit, what generic aspect of a language can be modeled by a context-free grammar? Thinking about the power of a context-free grammar. What is it able to accept or reject adequately? Any guesses? The answer is all syntax. Whenever you have a syntax error or think about syntax, that is something that a grammar can tell you yes or no. This is a well-formed program in this particular language. What's an example of something, maybe a line in Java, that a context-free grammar could not model? What word is most frequently paired with syntax when analyzing things? Different from syntax?
Grammar.
Grammar is a high level thing. But the answer to this is semantics. Syntax and semantics kind of go hand in hand. Does anyone know offhand the difference between syntax and semantics?
Way they're spelled. So isn't syntax like the structure, but semantics is the meaning?
Yeah. It's the difference between structure and meaning. So you can have a well-formed sentence that in English that means absolutely nothing. It has a subject, it has a predicate, there are noun phrases, verb phrases, and it makes perfect sense until you analyze what is this actually saying, and it's just gibberish. What's an example of a perfectly formed English sentence that is gibberish?
The no is yes.
So yeah, something like that. In a programming language, what would that be equivalent to? What is a line in Java that you could write that is syntactically correct, but semantically makes no sense? Or semantically just can't be done?
Like true
Like,
equals
for
false.
instance, the dog smoked under the pool is a great. Okay. I don't, okay. That's not something that you could go do.
Typing, like, you could theoretically, like, semantic or syntactically set like one variable to say an integer, but then set it again to like a string, and in some languages you can't do that
Yes,
semantically.
yes, that's exactly.
You wouldn't be able to find that out.
Is there anything wrong syntactically with char c equals 3.2? By the definition of an expression, we have a variable type, we have a variable name, that's a legal variable name. We're setting it equal, like there's a value on the right-hand side. It's just that when we go to put the right-hand side into the left-hand side, we find that we can't do that. We can't shove 3.2 into a character, we just can't do it. So it is syntactically correct, but it is not semantically correct. We call this type checking in general. And note that there's no way for a context-free grammar to express anything like this. It can only look at how well formed an expression is, or a statement is, or a program is. And this is well formed. It adheres to all of the syntactic rules of Java. In general, we'll find that semantics is a significantly harder problem than syntax. We can solve syntax with a grammar. Semantics will have to have a much longer and more difficult conversation about how we can model semantics. Nothing quite this simple exists, which is unfortunate because context-free grammars are beautiful. So this is one reason why we get different languages and language designs, is that people have been working on this problem for a long time, but nothing that everybody is happy with. So this is an ongoing discussion. If you find yourself interested in this problem, maybe you'll go and try to find a universally accepted way to parse semantics. But it's kind of an open problem. There are solutions, but not solutions everybody agrees on. All right, that is the end of this particular slide deck on context-free grammars. We're going to go into a very short one now. There's just a single problem type embedded in this, and that's that if we have a context-free grammar, we want to be able to produce a simpler context-free grammar. So how do we actually simplify these structures that we've been looking at? So we took a very brief look at how do we analyze the membership and parsing of context-free grammars. We're going to come back to the membership problem when we talk about CYK. But we looked at the feasibility of brute force parsing. The main issue there was that it had garbage efficiency. So we need something better than that. We need more efficient methods for this. But to be able to have a more efficient method for this, we're going to need to put our grammars in particular forms and make sure they are simple enough to avoid some of the issues that we would run into if we're going to have a simpler method. The assumptions of the simpler method are that the grammar is in a particular but equivalent form. So we're going to look at how to place some restrictions on context-free grammars such that it is simple and it is in a form that we can more efficiently answer the membership question for. Does that make sense? We want to efficiently be able to answer, is a particular string in a language, by looking at the grammar and the string and figuring out, can this grammar produce this string? We want to do that more efficiently than exponentially, so we need to manipulate our grammars first. So how do we do this? We've seen that there are equivalent grammars that can generate the same language, right? Just because your neighbor wrote a different grammar from you for a particular problem doesn't mean that you're wrong or they're wrong. You could both be right. One very easy thing we could do to simplify a grammar is to remove lambda. If lambda is a production or something that is accepted, we could easily remove this with a single simple rule. We just factor it out into a new start. If S was the prior start symbol, we're going to say that S sub 0 is the new start symbol, and we can either have the old start symbol or lambda. And that gets lambda out of the productions, aside from the start one. We can also have a substitution rule. We're going to look for productions of the particular form. There's a terminal followed by a non-terminal, followed by some terminal. So we have a non-terminal surrounded by terminals. If we have this particular setup, what it means is that we can look at the definition of the non-terminal and kind of move that upwards in the grammar. So maybe n is lowercase a or lowercase b. We could have two production rules here where we have T sub 1a, T sub 2, or T sub 1b, T sub 2. And that would be equivalent to this T sub 1n, T sub 2, where the n is the non-terminal. We just replace n with all possible definitions of n from the productions that define what n is. So here's an example. We have a grammar that says a can be defined as lowercase a or lowercase a capital A, or lowercase b, capital B, lowercase c. B can be lowercase b, capital A, or lowercase b. Wherever we see a capital A, everywhere we see a capital B in the first one, we can replace it with everything that it could be. And likewise. So take a second, see if you can produce what this would look like. Substitute every possible production for B into the production for A, wherever we see B as part of the definition of what A is. Does that make sense? So we have this line up here. We define this variable B. This variable B can take on this definition or this definition. So we can factor or move this up into this by saying, instead of this being a variable, let's make it every constant that it could be. And those constants could have variables, but note that nowhere is B self-referential. So we can completely get rid of B, this entire production, by replacing and making this have more ors in it. So it's just substitution. If we do this, then we can note that the entirety of the B production is not necessary. We can straight up delete it because nowhere in the grammar is there a reference to capital B. We have a definition for a variable that doesn't exist, so we can eliminate it. So the next thing we're going to go to is we need some kind of algorithm for being able to identify and remove productions that are unnecessary, like this B production. So let's talk about it. Are there questions on this process before we move on to removing unnecessary productions? All right. Here's another example. We have S is defined as ASB or lambda or capital A. Capital A is defined as lowercase a, capital A. how do we, or I guess, analyzing this grammar, are there any issues we see with it?
Lambda.
Lambda, we saw before. There's one big glaring other issue.
If you try substituting for big A, you just get more big A's.
Yeah, this is an infinite loop, right? There's no way to terminate this production right here. As soon as we say S is A, there's no way to create a string out of this, and we end up in a loop that just makes the string longer and longer and longer and longer, which basically means that there are zero strings once we move to A that are in the language because of this production. So A cannot terminate and produce a sentence, so it just loops forever. The solution is to remove the production entirely. It produces the same language, right? If we were to substitute for A, there are zero terminating strings in the language that it represents. So if we delete it, there are still zero strings that the thing that we're deleting can represent. So to figure out how to remove an unnecessary production, we have to first define this concept of a useful production, which will allow us to define a useless production. And then we can look for useless productions and stab them in the face. A useful production appears in at least one derivation to a sentence in the language. Makes intuitive sense, right? If we can use that production to generate something in the language, then it's used for something. If it does not, then it is useless. Every useless production will have a useless non-terminal, meaning that that particular non-terminal cannot produce any strings in the language or sentences in the language through any possible sequence of productions. So we have to look at every possible sequence of productions and be able to determine that it can't produce anything in the language. All right, practice problem. Steps we can go through. Which productions cannot lead to a terminal string? C. We see that C is defined recursively in terms of itself, with no possible way to terminate with all terminals. Any productions can't be reached from the start non-terminal. This is what I get for not hiding this correctly. It's apparent from the image. But from the start state, we can get to A or C. From A, we can't get anywhere. From C, we can only get to C. So there is no way to get to or define this B non-terminal. So just as here, you can draw a dependency graph. Vertices are the non-terminals. And edges are directed, of course, and represent one, that the production exists. And the from and the to edge leads you to where the definition is. So S can lead to A, S can lead to C, but we already deleted C because it can't lead to a terminal string. So C was deleted before we made this image. So S leads to A, and A leads to nothing. So if you draw this directed graph, this dependency graph, then you can quickly determine from there, if we can't reach it in a simple path, then there is no reason to include that non-terminal. Questions on simplifying context-free grammars? This is something we can always do to just make our grammars have fewer productions. Fewer productions is better. Note that, yeah, question?
Yeah, not a smart question.
That's fine.
What is a simple path? I don't know if you spoke.
Yeah, a simple path means that there are no loops. You start at the start and you just, as soon as you end up back where you start, you ignore that path. You don't branch that path. Because otherwise we never terminate, we would be infinitely looping S, 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 S. So we're basically going to add to a visited list every vertex that we have seen so far. So we start with S, add S to visited, have A and B in our unvisited list. We're gonna say everywhere we can get from S, we can, and we only care about unvisited nodes. So S can lead to S, but because S is visited, we ignore that. S leads to A, so we go A from unvisited to visited, and we look at all edges out of all visited nodes that we just visited. With A, there are none, so we terminate, and we see that there exists a B that we never got to. Anything else? Clarification questions?
Guess I have one.
Yeah.
Do those edges need labels for the characters in that kind of graph?
It's easiest to visualize from the non-terminals. You're talking about terminals or non-terminals?
So like when S goes to A in that graph.
Yeah.
Does it not really matter, like how it got there, like what?
Yeah, it doesn't matter. We're not producing strings. We're just drawing a dependency graph to show that either things are reachable or unreachable. That's the only question we are answering, is to try to figure out, are there productions in this grammar that we can eliminate?
Okay.
Excellent questions. This is the world's shortest unit. I just threw this together and was like, should I just addend this onto the end of the last one? It doesn't matter. So yeah, there are 4 slides to this unit. This one will be much longer. And by much longer, it's not in terms of slides, but the density of the material. Okay, so we talked about removing useless productions, but now we're going to start talking about some forms of context-free grammars that are useful and used for particular purposes. So some forms that we can talk about for grammars are standardized and used to, for instance, create grammars without ambiguity. They can also be used for other reasons, but there's sub-problems that are useful either to compilers or to other applications of automata and languages. So the first we are going to look at is called Chomsky normal form, which is just the best name. I wish my last name were Chomsky, because how much fun could you have with that? So any context-free grammar without lambda in the grammar has an equivalent grammar in Chomsky normal form. So we talked about how to remove lambda from the start, at least. So we'll go into exactly how to change a grammar into Chomsky normal form. Chomsky normal form will place some restrictions on the number of terminals and the number of non-terminals in each production. And we will show that we can have this equivalence, any other grammar could be shown in Chomsky normal form. And that will allow us to simplify some of the algorithms that we will discuss that talk about things like membership. What's nice is the conversion into Chomsky normal form, which is why it's so used. It's very straightforward, very algorithmic. This is the most used context-free grammar form. There's one other form that is important for one kind of proof that we will talk about, or one kind of result, I guess, that we will talk about, and that is Rybach normal form. So just like Chomsky normal form, there is an algorithm to convert into Rybach normal form, and again, it places some restrictions on where terminals and non-terminals can appear in a production relative to each other. The algorithm is not as straightforward, which is why it's not as well used or as frequently used as Chomsky normal form, but it will be an important result. So it is important for us to go over Rybach normal form so that you understand Rybach normal form. I probably won't have any homework questions or exam questions on it, but it's important to understand just so we can use it to derive another result. The important one is Chomsky normal form. If you've ever heard of CNF, it's usually abbreviated CNF. So I'm gonna start abbreviating quite some of these longer terms. So CFG is a context-free grammar, CNF is Chomsky normal form. These are the following legal forms in CNF. We can have a non-terminal lead to exactly two non-terminals and no terminals. The other legal form is a non-terminal leading to precisely one terminal. And these are the only two allowed rules in any grammar in CNF. Non-terminal to two non-terminals, note that there can be repetition, A can lead to AB, that's allowed. Or it can lead to a single terminal. So go ahead and spend just a couple minutes, write any grammar with at least 4 productions that adheres to CNF. As a game designer, I now suddenly want to put a creature kind of like a Pokemon inside of this game that is called Chomsky. It has a really big mouth. And then it's going to have a normal form and a battle form. Embed all of this inside of it. Anyway, this is what my brain does.
Did you ever play that game? It was called, it's like something is you. Do you remember what I'm talking about?
I know
Baba is you. Baba is you.
Yeah. I have not played it, but yeah.
It's reminding me, this is reminding me.
Yeah. So the next thing you should do if you have your CNF grammar is to take a look at it and see if you can figure out what language it represents that you've written. Or try to think about why is this form important? What does this form allow us to do that a grammar without these kinds of restrictions would allow us to do? Just try to think a little bit about this form and why it might be used.
Plus for branching, but.
Yeah.
They said it's good. Also, I didn't say it was gonna be useful.
Your tree of choices.
Yeah. So we can apply quite a bit of computer science theory to grammars in this form because we can't have ridiculously complex productions. They are very simple, straightforward, to the point. we either have an internal node with two branches, or we have a single child that is a leaf. That allows us to do things like split apart the B and C and ask about, all right, what could be generated in the middle of this? If we have a BC, what could that represent? And that's going to expand in a binary tree fashion.
It seems like. I don't know, I was only right grammar that accepts one string.
A grammar that accepts a single string, you can totally do it.
Well, I don't see how you would do one that accepts multiple strings with these rules.
Oh. A leads to BC. B leads to BA,
But then that's the B permanent.
and then C leads to something that is. You can define B in multiple ways. There's not just a single, you can still have it the same way as a non-terminal on the left
That
side.
makes sense.
Yeah,
I didn't,
Can that terminal at least be lambda?
we don't want lambda anywhere in
Okay.
there because we need a theoretical guarantee that if we see a non-terminal, it leads to at least one terminal.
Okay.
If we have lambda there, it can lead to zero terminals, which will break a lot of what we're gonna talk about. It's a very important assumption. All right, so the process of converting into Chomsky normal form. All right, we need a grammar without lambda or productions with the right-hand side a single non-terminal. So something like A to B. Those are important and those can also easily be eliminated. So we've discussed before methods for removing these from a grammar and keeping it equivalent. So the input to this just assumes that those prior methods have been done and the grammar is in this associated form. Step one, we will construct a new grammar from the input grammar. So we're going to be parsing the input grammar and producing a new grammar as we go. We will start by looking at all possible productions of some non-terminal to a list of terminals or non-terminals. If the size of the list is 1, it must be a terminal. So we know this. So we'll introduce new non-terminals for each terminal in the production. Whenever we have a terminal, it should always be represented by the same non-terminal symbol. So we're just changing variable names, basically. Substep 2 here, for each new non-terminal introduced in step 1.1, we'll add some additional production, some non-terminal to some terminal, converting each of those non-terminals to their associated terminal representations. Don't worry, what's coming next is an example. So this, by the time we're done with step 1.2, no terminals left in any production with a right-hand side length greater than 1. We've taken everything down into length 1. In step 2, we will introduce new non-terminals to reduce the length of each long production of non-terminals. So we have potentially lots of long strings, so we're going to just start chopping them into pieces of 2. So every production that involves non-terminals has some list of non-terminals up to length L. So we can introduce up to L-2 new non-terminals that we're going to list as capital C, up to as many of them as L-2. We can add some additional productions to the grammar at this point that basically say we're going to start with a single non-terminal n, and that is going to map to n sub 1, which is the old production here, n sub 1, and the new one, c sub 1. And then the next one will be c1 is defined as n sub 2, c sub 2. C sub 2 we define as N sub 3, C sub 3, etc. until we end up with C sub L minus 2, which will take the last two N sub L minus 1 and N sub L. And this will give us an equivalent grammar. You can then remove any old productions that aren't in Chomsky normal form. And I would argue that the resulting grammar is in Chomsky normal form. Like the hard part here is at the end, just kind of seeing why this works. Hopefully this comes through in the example. We'll probably have to breeze through this example with 2 minutes, but we'll go over it again at the start of next class, just to make sure that we don't rush this, because this is not something that should be rushed. All right, so the example is to convert the following grammar into Chomsky normal form. We have these associated non-terminals, productions. So we're going to introduce some new non-terminals representing A, B, and C and replace them in the old grammar. So step one, we're just producing some new rules that lead us to all of the terminals in the language. Note that right now they're useless because nowhere can we really derive these. Well, you do see that we replace the lowercase a's in these with the B sub A, B sub B, B sub C. We've removed all terminals now from the original productions. So straight to terminals, replacing all terminals here, A and B and C, with their associated rules. Once we do that, we introduce variables to get the first two productions into normal form. Because note that this one's already in normal form because there are two non-terminals. A non-terminal is defined as two non-terminals. So we need to start splitting. This is 3, this has 3. So we're going to split this into, you can see that we have new rules, D sub 1 and D sub 2. D sub 1 is this B sub A. D sub 2 is B sub A, B sub B. And then if we do this, then we have removed a single one out of this, where S is now defined as A, D sub 1, and A is now defined as B sub A, D2. And that means that the entire grammar now is in the associated form where every non-terminal is defined in terms of two non-terminals or a single terminal. And this grammar is equivalent to that one, which is equivalent to that one. So we're out of time. We'll let this sink in a little bit and we'll come back to it at the start of tomorrow's class. Talk a little bit more about the intuition and what this can let us do. I saw people still taking notes. It's like, I need to get through the next slide, but I know that there are going to be places where people want to take this.
I think I once we get this, it has to be a cleaner digest, not a lot of stuff. These six, there is a clean side, it's just. Yeah.